Hello. Welcome at the lesson 4 session. Thank you for joining me. I think I can see everyone. Okay. If you can hear me, yes, thank you. Hi. Okay, let's start our session. Before we start, I can tell you that this is the last week before the first midterm test. Okay, the first, all of the exams, two midterms and the final are the proctored test. That means you have to make your appointment at the Examity. All of the information you can find on Canvas on our site. You have to make an appointment. The test, the midterm one, will be open next Thursday and will stay open until following Monday. And during that time, like any day, any time, you can take that test. And it will be still through Canvas, but you will be not able to open on your own. You have to have an appointment at Examity, and the proctor, the person there, will help you to open the test. Okay? And will be exactly the same style, the same type of questions like the weekly assignments. You can definitely check the practice, the sample tests, which are placed in the next module, the module of the midterm one. Okay? Which means next week we will have no new concept, no new content, just the review. And I will probably hold the same hours. Okay? Tuesday and Wednesday. If something changed, you will definitely get an information. I will send an email. But no new stuff, just the review sessions. Yeah, Caroline is we're not doing any, but I can try to add additional session. And we can do this as a recitation session, which will be just like practicing, just solving the problems. We can try to find out the night, maybe even the Thursday night, but you have session with the GSCG leader on Thursday. Okay, I can try to think about this, okay? And I can add the recitation session to our weekly sessions. Okay. Okay, that's mean what left. We do have still a few applications of integrals, which is section 5.4, work. We will try to compute some work today. And tomorrow, the section 8.3, which is another application, like we will talk about the pressure, force, center of mass. And that's just still a little bit of integrations. The thing is, like, in order to compute like the work of force, the numbers are not always as friendly as we will wish. That means when you will do your homework assignment, you may use the calculator, but it's just like the simple function, like multiplying the numbers, just this, because will be decimals. But I promise on the weekly assignment you will see this week, and of course on the midterm I will create the question that you don't need the calculator. Okay, if the numbers are not good, we will stop at some point, and you have to, like, let's say you have to present your answer like a product form, like 26 times 9.8, for example, and you don't have to multiply. Okay, that's we don't need a calculator, don't worry, because somebody asked me if we will need the calculator, and makes sense. And I did use the calculator for today's session, but as I said, don't worry, you will not need a calculator. Okay? You will probably just set up an integral, and that will be the final answer, no evaluation required, because I would like you to know how to apply. Okay, let's start. Oh, of course, I would like to say again, thank you for your really good participation on the discussion board. I still didn't grade it. Yeah, I will probably grade this afternoon. I will read all of your comments. I read some of them, and I'm really, really impressed, positively impressed, okay? Because some of your posts, like some of your answers are fantastic, excellent. Yeah? And of course, this is also a good sign for me, because as soon as if you can explain a question, if you can like teach someone, this means that you really understand. Yeah, that's good. That's a good signal for me. Yeah, okay. Okay, that's what we have. Work. Of course, work, but we will look at more rigorous way, yes? But work, we know what work is. It's just to perform a physical task. It's a work. Not even physical. Yeah? Even if we have to learn something, is also work. Okay. Oh, a little bit too tiny. It's okay, we can leave it. I don't know if my slides. Okay, that means the term work is used in everyday language to mean the total amount of effort required to perform a task. Yeah? I think I took that sentence from your textbook. It's a beautiful sentence, beautiful definition of the work. In physics, it has a technical meaning that depends on the idea of the force. Okay? That means, first of all, we have to define force. Yeah? Like force means like a mass times the acceleration. Yeah? Mass times the acceleration. And then work is that force times the distance, yeah? On whatever distance we're doing. Like intuitively, you can think of the force as describing a push or pull on an object. Yeah? For example, a horizontal push of a book across the table, or downwards pull of the Earth's gravity on the ball. And thousands of examples. Okay, cool. That means now we do have a few formulas that maybe you remember from physics. If you didn't have physics, I can explain things. That's my pen. That means, as I said, first of all, we will need to know how to define force. Okay, and force, as I said, is the mass times the acceleration. Okay, and this is just the Newton's second law of motion as a product of the mass and its acceleration. Acceleration, of course, is the second derivative of the position function. Oh, this is just a different, I did use the Leibniz, the different notation. But second, acceleration is the second derivative. It's the rate of change of the rate of change. Okay, and then we will have a few units involved. Okay? Don't worry, it will be not so heavy, okay, I promise, just a few types of question. Okay, that's of course, you probably know the SI metric system, which I like to use the metrics, but not always we're using the metrics. We're also using the US customer service, which is like the pounds, foot, feet. Okay, that means metrics means that we will measure things in kilograms. The distance is in meters. Yeah? We have to remember kilograms, meters, time, it's in second. And then when we take, because we can see the force is defined as a mass, which is kilograms, and then acceleration is the distance over the time, which is meters over the second, and again over the second is the second derivative. That means kilograms times meters over the second square, that's the force unit, and it's called like newtons. Yeah, you probably have. And I just copy like a picture of the SI units, just in general. Time, we can see second, length, meters, mass, kilograms. We will not talk about the electric current, but it's ampere. Temperature, actually, it's not Fahrenheit, not even Celsius, it's the Kelvin. Okay, amount of substance is mole, like for the chemical particles, and luminous intensity is candela. And that's it, that's just the units. But we will focus, of course, on those. That means 1 Newton means that the force of 1 Newton acting on a mass of 1 kilogram produces an acceleration of 1 meter per second square. Okay, but we will also have a questions with the US units. I call like US units, which you will see everything like in pound, like the weight will be in pounds and the length will be in feet. Okay, so let's see how we can deal with this. Okay, That means again, in order to, oh, hang on, no, that's force. Okay, please remember, please make sure that we know this formula: mass times the acceleration. And then what we have to actually focus on, work. Okay, that means work, it's simply a force times the distance. And that means this is a definition of the work. We have to find the force, and then what force we applying the force on the certain distance. And again, force is measured in newtons. Okay, that's we know this. This will be a newton, and distance is in meters. Newtons, and we can call like Newton meter, but actually we also have another name for the unit of work, which is joule. Okay, we say J, but we saying joule. Okay, that means it's newtons times meter. Or we may have a work, yeah? I mean, first of all, force measure in pounds, okay, and distance in feet. That means we will have, because force as a weight, okay, that means weight is different than mass. Mass is just mass, but weight involves that acceleration, acceleration of the gravity. That means force will be in pounds and the distance will be in feet. And then when I compute work multiplying force times the distance, then I have foot-pound. And then we don't have to involve any acceleration. Okay? Which is, yeah, that means like foot-pound is about 1.36 joules, but we will not convert, just to know the units. Yes, yes, it will be, okay. Always the introduction, because it's more like physics, more like engineering application. Yeah, I can show you probably 3 different types of question, okay? And we will just focus on this. That means for example, let's see this one. How much work is done? Okay, yes, yeah. Okay, that means if you took physics 211, yeah, then you should be, that's probably the basics for that physics class. Okay, now let's take it easy, okay, I promise. Because this is, it's actually calculus class, right? But we have to still know some applications. Okay, how much work is done in lifting a 1.2 kilogram book off the floor to put it on the desk that is 0.7 meters high? Okay. Use the fact that the acceleration due to gravity, this is important, the acceleration to the gravity, yeah, it's 9.8 meters per second square. So we have to, I will probably always provide that number if you need. And then how much work is done in lifting 20-pound weight 6 feet off the ground. Yeah, that means we can see A and B, we do have different units. That means let's see how we can compute this. This will be A. Did I type? I typed this. That means we have to remember this. Work is force times the distance. And force is mass times the acceleration due to gravity. Okay, that means this is the formula for force. And now, no problem, let's just substitute. Yeah, that we can see we have to know these formulas. Okay, let me just force times distance, and force is defined as a mass times acceleration, which is the acceleration due to gravity in this case. Okay, 1.2 kilograms, 9.8 meters per second square, and the distance, right? The distance. Yeah, and of course you can probably imagine, I did use the calculator, but as I said, if I will ask this question, this will be your answer. You don't have to multiply. Okay, maybe the units, because we have perfect units, kilograms times meter over the second square. That means what I did, I compute the force, which I can maybe use the same. And this is the number, that's the force, which of course, this will be a Newton. Okay, kilograms times meter. But again, I would ask you to leave the answer like that. Or you will see the calculus application and then you will see. Okay, header is, what's confusing me is that we are using M for meter. Ah, you're right. Yeah, okay, that means first of all, you can see that arrow. I did this because your textbook actually is doing like similar. I always trying to correspond my slides to the textbook because you can read the textbook and then it's easier. You're right. Normally, we will not even put probably the all of the units. Okay, that means you're right because I'm saying M as a like a label for mass and M as a meters, as a units. Okay, as soon as we have the formula, we have to just think that that's, of course, M mass. And as soon as we see the units, we have to think that is unit, the distance, the meters. But okay, I don't know how, but don't worry, we will not have this, we will be not confused. Okay, we will not confuse. I know, probably I say, yeah. Yes, if we, no, we will not convert between like kilograms and pounds. No. If the question is like part B, which I will show you part B, if everything is in pounds and feet, then we will just do different way. If it's in kilograms, meters, seconds, then we will do this way. Okay, and okay, that means let's see what I did. I just multiply 1.2 times 9.8. I've got this number, and that's the, oh yeah, I actually type this because it's important. The green part is force, and it's in newtons, and then I still multiply 11.76 times 0.7 Newton on meters, which is joule. Yeah. 1.2 kilograms is actually the mass. Yeah, it's kilograms. That means it's a mass. It's not a weight. That we have to acceleration. Yeah, acceleration, of course, is the acceleration or due to gravity. Yeah, it's gravity. It's gravity, but we do have acceleration due to the gravity. Okay, but we can see if it's SI units, if it's metrics, we will do this way. Yeah, that's the same thing. M times A or M times G. Yes. Acceleration, but if we will always talk about this one. Yeah. Acceleration due to gravity. Or we can say gravity in short, but it's the acceleration. Okay, and then when part B, it's everything it's in pound and feet, we can see we have the same formula. Work is defined as a force times the distance, and we just simply substituting because the force in this case is that 20 pounds, which is weight. That means includes everything. We will not be worried. Did I type? Okay, that means I just have 20 pounds times 6 feet, 120 feet. Did I write? Hang on. Yeah, like a feet. I have some calculations. Feet, pounds. Oh, that's my other explanation. That's my, and we can simply leave the answer like that. This one, of course, was much easier. Okay, no, and then we will, because that 20 pounds, as I said, includes like it's a weight. That means includes the whole acceleration part. Yeah, we don't. That means it's a little bit easier. Okay, that means you can definitely check these basic questions because I can ask. Yeah, we can see it's so basic. Maybe the part A has, yeah, but if I will give you different numbers, it will be so easy to do it. Yeah, but that just please remember that the kilograms times meters over second square, this one is Newton. Newton times meter is joule. That's it. Okay. And then I was trying to, that's the same thing, but we can see in part B, we didn't have to multiply by G, by the acceleration due to the gravity, as we were given the weight. which actually is the force and not the mass of the object. Okay. Okay, that's me now. Everything was fine, and we will use the formula for the work force times distance if the force is constant. But of course, not everything is so simple. Not always the force is constant. We may have a force as a new function. That means we may define force, let's say f of x, that will be different, not always the same, not always like the same force. It will change, it will vary. That means what we will do, don't worry, I can show you a little bit of calculus, which you probably know. Do you remember slicing and adding together infinitely many items? That's integration. That's what we will do. I can show you maybe the whole. Oh no, okay, let's stop here, and I have few formulas. You have to just remember the formula. That's what you can imagine, that pink curve, it's actually the force. I can say f of x, it's my force. Yeah, I can say f. And we can see it's different. And we would like when we will be moving the object from A to B, we would like to compute the force. Okay, which of course, like for my sample points, if I will, of course, slice, like this will be the force, this will be the force, that's the force, that's the force. Now, in order to compute the work, I will multiply by the distance. Distance times the force. Distance times the force, which is the value of the function. That's we can see value of the function, which actually, where is my... Oh, I can write that. That means in order to find the work, we will multiply a function times the distance, because we can see we will divide by equal subintervals. Okay? And this, yeah, I'm just using this weird notation, but this means like a sample points, x sub 1, x sub 2, that we can say x sub I. Yeah? Because it's at some point, I will find the value, and I will just multiply delta x times the value of the function, which is the distance times the force, distance times the force. Okay? And now we remember this. This is distance times the force. And when I add sigma, means that I am adding all of them together. Okay? And the perfect approximation will be if I have infinitely many of these subintervals, or saying differently, delta x should be teeny tiny. Or number of the slicing, we can say this way, it's like infinity. That means when n is infinity, n is number of these subintervals, we're using the limit, and we remember limit of the sum is just the integral. That's mean now the final output. In order to find the work, okay, if the force is like a variable, we will just integrate on the given interval, the formula for the force. And of course, dx means that the distance, yeah, that's the distance. We're integrating, we're slicing and adding together the x-axis, the interval that we need from A to B. Okay, that means this will represent, that's what we have to know. I was trying to explain a little bit of definition, but this is the formula for the work if the force is not a constant. Okay. And, oh yeah, that's the same thing. That means please, okay, just this. Okay, if you don't remember, okay, and let's try to see how easy, like ironically, is even easier question. When a particle is located a distance x feet from the origin, a force of x squared plus 2x pounds acts on it. Okay? That means this is the formula for the force. We can see it's changing, actually parabola. How much work is done in moving it from x equals to 1 to x equals to 3? Yeah. That means what we can do, we can simply say that the work is just the integral, definite integral from 1 to 3 of this. And we can even integrate this. I can probably draw this because I don't have x squared plus 2. It's parabola. We don't have to even draw it, but I just want to show you if I factor out x, I will have 0 and -2. -2 and, no, it's open up, open down. Can you tell me, is this parabola open up? Thank you. That means I will draw it like that. Okay, that's -2, that's 0. And then we moving from 1, it's actually not a line, to 3. So we have to just find, theoretically, the area of that part, which is just there. And of course, if this is force and this is my interval, distance times the force, distance times the force, and we know it's infinitely many of this delta x. Okay, we can integrate, but as I said, probably I can ask for this. I mean, this is so easy. I might ask you to evaluate, because that's not a problem. X cubed over 3, x squared, substituting upper limit 3, substituting lower limit, and I hope I didn't make any mistake. 27 over 3 is 9, that's 9, 1/3 and 1. Subtracting because we distributing negative. Okay, 18, 17, 16, and 2/3. And then everything was, and you can see, don't worry for the units, you can just say, oh, this is like, I'm just trying to, where's my notes? Yeah, because sometimes I make the other way, but this is okay, foot pound, because everything was in pounds and in, yeah, and in feet. I'm just looking for the distance, feet and pounds. Okay. That means just to integrate. Okay, but let's make a little bit harder. But that's it. That's let me example. 1 second. I just want to. Okay, that was example 1. That means this will be on your weekly quiz. Okay, and then example 2. Oh, yeah, I type this. Example 2. Okay, nice and easy. Okay, now let's see. Also what we have something, because in the next example we will use another physical law. We have something like Hooke's law. And what it is? When we have, again, don't worry, we will, yeah, you will be able to do it. When we have a spring and some, some weight attached, and that's when we can see some block. We have the spring, and we know like spring works. Yeah, it has its natural like length, natural position. Okay, but then I can also stretch it. Okay, that means we do have the force required to maintain a spring stretched x units beyond its natural length. It's proportional to that distance. And then that's force, okay, this is force, it will be defined as a k times x. Okay? That means it's that k, that coefficient k. When k is a positive constant, call the spring constant. That means the k, like depends, if k is big, probably the spring has like a, then the spring, let me just, if it's big, probably it's not easy to move it. If it's small, probably it's easier, okay? That we can see, in order to move from 0, from its natural length, natural position, or x units. Okay, that means we will define this the coefficient. Okay? And normally the distance, of course, it's not large, yeah, because we know how spring works. We can't really go too far, because then we will destroy the spring. We will not come back to the normal, the natural length. Okay, but this is important. We do have a coefficient k, and let's see how we can calculate. That means this is example 3. Okay, the third question. A force of 40 newtons is required to hold a spring that has been stretched from its natural length of 10 centimeters to the length of 15. Okay, that means from, yeah, we will call 0, but in this case will be 10 and then 15. Oh, my pen sometimes does this. Okay, that means this is the natural, because we always say the natural length is actually 0, but we still want to refer to the origin. Okay, that means from 10 to 15. In order to stretch from 10 to 15, we need 40 newtons. Okay, how much work is done in stretching the spring from 15 to 18? Okay, that means now we have to go even further, 18. Okay, we have to move it even further. That means, first of all, we have to find out, okay, we have to find out what is that coefficient k, because I need my function, my force, okay, I need my force kx. This will be the formula. As soon as we have a spring question, we have to think that this is the formula, kx, but we have to find out the coefficient k, like, because that, yeah, the force of 40 newtons is required. That means what is this coefficient, how this is referring. That means I will, of course, use that kx, and now let's see what is given, or the units. Okay, because everything is in centimeters. That means now we have to think, we have to convert from meters, okay? And we know that 100 centimeters is 1 meter. Now 15 centimeters will be, okay, let me put x for now, just I would like to show you how to convert, okay. That means you can remember that 100 centimeters is 1 meter. Okay, 15 centimeters is x meters, we don't know. And then we can cross multiply. X times 100, 1 times 15. Then x, don't put any units because my units corresponds centimeters underneath centimeters, meters, meters. And then I can divide by 100. And this means 0.15. And since, yeah, it's x, it's in meters. That means 15 centimeters is 0.15 meters. If you know right away, of course, that's just how to convert. Please remember that 100 centimeters is 1 meter. Okay, that means now what we know. We know that the force, okay, that we can see force, 40 newtons, okay, is required to stretch from 10 to 15. That means what is this distance? It's just 5 centimeters, which is 0.05 meters. And that means when the distance is changed, yeah, 5 centimeters, 0.05 meters, then the force is the force is required 40 newtons. And then let's see, that means I can say my force is kx, that means force is 40, k is k, x is 0.05. And having this equation, I can calculate the k, the coefficient k, from the Hooke's law formula. I can just divide both sides by 0.05. And 40 divided by 0.05, I can say, because 0.05 is 5 over 100. Dividing by 5 over 100 is multiplying by 100 over 5. And 5 divided by 40 is, I mean, the other way, 40 divided by 5 is 8. 8 times 100 is 800. Okay, that means I do have a coefficient, 800. Yeah, that means 800x will be my force. But we can see we had the force given on the given distance, just 5 centimeters. And then I calculate K and I substitute it back to the formula, Kx. And now maybe you can tell me, I know you're probably scared, but no, don't worry. You can tell me how much work is done in stretching the spring. And I can tell you that the work it's different, right? It's variable. That means, do you think you can tell me the formula? It's not just, it's changing, it's the variable. We can even see the force is changing with respect to the distance. We do have a coefficient, we have the formula. That means if the force is a variable, what formula for work we have to use? Hopefully you... okay, but what okay, Dave, yeah, because, okay. How much work is done in stretching the spring from 15 to 18 centimeters? That means we definitely have the distance 3 centimeters, which is 0.03 meters. But what I'm saying, this is my distance, which I can still say my interval will be from 15 to 18. I mean, parallel, from 15 to 18, okay? And the force is, oh my gosh, if I would like to draw this line, 800x, such a big slope, yeah. And then I have to, but I have to evaluate from 15 to 18. That's my point is that we have to integrate, okay? Not just doing this. We have to actually integrate. Okay, we have to integrate the force formula. That's my point. If the force is variable, we will integrate the force, okay, on the given interval. And now let's see if I choose. That means what I did from 0.5, which is from 5 centimeters, because now we have to be careful because this is still like my natural position, 0. Okay, that means this is my 5 and this is my let's see this one. This will be 5, that will correspond to 5, and this will correspond to 8. I know that this is 10, but with respect to the natural, I really have to see that I am at 5 centimeters away from the natural position to 8. Yeah, that means this is just that distance. Then we will have a little bit different way because we have to make sure that we can't even say from 15 to 18 centimeters. We have to say, because then the zero is important. We just move it, like how far, how many units we going from the natural position? 5, okay, that means 5 centimeters, and 8, which means from 5 to 8. Okay, I would say this is the 5 centimeters and 8 centimeters. If we will do from between 0 and 3, I think we will get different. Makes sense, but we can't really say 0 because 0 is the natural position. We don't even need any force. Okay, the force will be 0 as soon as I move to 5 units. Then I need that force. You can even see we even have 5 here. Yeah, 5 centimeters. That means from 0 to because everything is at 10. That means we have to respect. Yes, we have to respect this. That means this is actually now. That makes sense. It is 10. It's given, but we don't even we still consider this as a 0, the natural position. No work, no force. But then I need to move 5, and then how much work is done by stretching from 5 to 18, even further. Okay, and we know the function. That means, yeah, this is just I know it's a little bit, but the force of the spring is exponentially greater. Oh yes, of course. But no, why exponential function, Dave? Not always. Yeah, we can go, but no, we will not. Because as like we have to say that the natural position is 0. And that's it. And we're moving 5 centimeters and then from 5 to 8. That's the reason. This is from 5 to 8. Because it's different. Yes, the work will be different because we still have this the stretching like how can I say, capability, which is actually the coefficient K is telling me. Yeah, that's me. No, we can't really, we have to go. I just want to explain this. We can't say 0. We have to say from 5 to 3. Okay, and you can see like we know where the 800 came from, and just differentiating this, integrating 800. And I think I didn't type my work, but you can try to integrate, but as I said, I will ask you to set up this integral only. Okay, just to know, that's mean the 5 centimeters and the 8 centimeters. I want you to know, yes, to know this. This is centimeters, my pen. I don't want to say meters, centimeters. Okay. And when you know how to integrate, we can even integrate, but the units are in meters. I can change from 5 to 8 and then probably will be easier. But if the numbers are too small, 2 decimals, too crazy, we will just get it's exponentially greater than 15. Why the limits? I know you add the 10 because it's just the like you can see like that, because this is not even, I mean, it is important, but it's not important in this content. 10, it means that 10 centimeters, but this is the natural position. Yeah, that's the natural position. Could be 10, could be 20. That's kind of like that. The spring will like stop with that weight. Okay, we don't even count this 10. 10 is actually 0. Okay? And we're stretching from, because we will always have some length of, I mean, we will always have this distance, of the spring. That's mean I can't really say 0, 10 centimeters. And then everything starts from there. Yeah, makes sense. That means 10 could be 20, could be 50, could be, depends on the of the size of the spring. But 10 is just information, but we're not using in this calculation. It's 0. And then we're stretching, 5 centimeters, and then to 8, from 5 to 8. I hope this makes sense. Okay, I don't want to make things complicated. Okay, and then, okay, let's solve this question. That's mean what I can do just to make, because okay, let's solve this question. And I have the last question, and I am maybe okay to skip that question. Okay, I mean that, but let's see. This one we have to know, because it's similar thing. Okay, that's me now. We don't have any spring, but it's similar concept. Let's see. 200 pound cable, that means we have the weight, is 100 feet long and hangs vertically from the top of the tall building. We can see. How much work is required to lift the cable to the top of the building? Maybe you can tell me. I can, again, the force, because we have to just find the force. Yeah? We have to just integrate the force with respect to the distance. And that means how, like, yes, what will be, we have to, I type the solution, but I can integrate the force with respect to distance. This is, of course, the distance. Yeah, like I can, that means we will integrate, and we always looking from 0 to 100, because it's 100 feet. We have to pull it. Okay? That means from 0 to 100, because I'm assuming that I'm on the top from 0 to 100. But the thing is, what is the formula for the force? Yeah, that means let's make it a little bit easier maybe. Yeah, we have to integrate because it's different, the weight and everything. That we have to, force, of course, is, it's the weight, okay? It's the weight, but we have to know what is the weight of 1 foot. Can you tell me what will be the weight of 1 foot? We can still, it too, yes. That means it will be just, we can use the same thing. I can say kx, because we will have this again, this like the coefficient, yeah, of that weight. That means we can see 200, that's the force or the weight, yeah? And it's 100 is the whole distance, the length. That means k is 2, okay? That means my function is just 2x. Yeah? We just need 2 pounds per foot. Okay, that means 2x. Make sense? And you have to just integrate 2x from 0 to 100. Do you think makes sense? Okay, I just, yeah. Okay, I can erase this because, of course, I want, oh, okay, good. Let me erase. That's how I would like really quickly understand. That's how I would solve for myself. But of course, for my students, I want to be more details. That means we okay with this, yeah? 2 pounds per foot, which means, yeah, I was trying to be exact. That means the force will be, because since we're trying to, again, slice it and find the force for every single part of that cable, which will be two times per that distance. Yeah? 2 pounds per foot, per that distance. And then the work, of course, is force times the distance. And that's the force. Yeah? That's the force. 2 pounds per distance. And this is like the entire distance. Yeah? But of course, that's 2. And I switch this. And then we adding, because that's what I did, like every single distance. But then I'm adding everything. But we can see, if you okay, from computing this, which actually we got 2x, and jumping to that step, I'm perfectly fine. But sometimes here we would like to have more details. But if you understand that we have to integrate, if the force is like a variable, and it is because it's changing, okay, then you can just understand that you can just write down that we have to integrate the entire distance and we have to integrate the force. But make sure that we have a good formula for the force. And I think that's the easiest way. Yeah, we know how we got that too, because it's 2 foot. 2 pounds per foot. That means we have to include that too. Okay. Okay, let's see. Okay, and I did calculate 100,000 foot pounds, but that's fine. I'm just really interested in that integral. Okay, and then, yeah, that's the solution. You can probably, I was typing my thoughts. But then I have this question. And as I said, do you think like just the basic formula for the work and force and the spring, the Hooke's law and the cable, do you think that's enough for this section? If you will tell me yes, I can skip this question. It's of course beautiful question because we have some, but then I can skip it and I will not include this in the weekly assignment and I will not include in an exam. I can ask you, you can tell me, or I can go through this question. Oh, everybody is scared. Skip. Okay, Jacob, you brave. Yes, you brave. That means if everybody, I do have a solution, because that's what I would like to. Depends on the, of course, on the instructor. Some, but we would like you to know this, and you will have the solution. But I will promise I will not include this. Okay, because it's better if we focus on it's. I just realized that it's like too many units, maybe not too many formulas. Okay, but just just. Okay, that means we will skip this. That means I will go for, but I still want to solve, or you will tell me. Okay, okay, no problem. I just want, I don't want to make your life. Okay, that means don't look at this. Density, volume, you know the volume, pi r squared times the height. Do you remember the slice? But we will skip it. Mass times the gravity. It's beautiful question, but and then again we did, but please, yeah, please just see we integrating a force. Okay, the thing is we have to get a good equation for the force, but please remember, in order to get work we will integrate the force. The thing is we have to get a good formula for the force, depends on the scenario. Okay, that means this was my last question, or this is just the solution. But before we finish, I have a few questions, okay? And this is from your textbook, and this is actually the recommended homework. That means let's answer a few questions. Can you tell me this answer? I mean, can we solve this question? I think I will. That means we do have 360-pound gorilla climbs a tree to a height of 20 feet. Find the work done if the gorilla reaches the height in 10 seconds and then in 5 seconds. That means, what do you think? What will be the work? Okay, because I'm asking for the work. Can you tell me the formula for the work? Do we have to integrate? Yeah, it's just, I mean, we will use mass times the g, the gravity, the acceleration due to the gravity, if we see the metric units. If we see the pounds and the feet, this means that the weight is, that's given. That means force times the distance. Okay, that means that's, and of course this is, I don't need to, that, because that's the weight and this is the distance. Okay, because this is simply like the force, it's not a mass, it's the weight. Okay, it's the weight. Okay, that means that's the only thing that we have to do. 360 times 20, and this will be like feet, pounds. 36 times 2, 72 and 2 zeros. Feet, pounds. Okay, that means that's the work in the feet, pounds. But do you think it will be different answer for A and different answer for B? No, yes, no, yes. It will be the same, yeah. That's, we can see, doesn't matter if, of course we can compute different parameters, different like different things in this scenario, but doesn't matter if the gorilla will climb in 10 seconds or the 5 seconds, the work done, it's the same. Okay, it's exactly the same, because the formula for the work doesn't depend on time. Yeah, no time. Okay, and then let me check this one. How much work is done when the hoist lifts 200 kilograms rock to the height of 3 meters? The same, everything is fixed, no function. Work, it's simply the force times the distance. And now, because this is mass, okay, that's mass, 200 kilograms. That means how we will compute force. and distance is 3 meters. Distance is just 3 meters. Yes, that's we have to put mass times gravity. Acceleration, which this will be 200 and 9.8 meters per second, and I will provide for you this one per second squared. Okay. And if you like, you may skip the units. I'm just trying to be helpful for the header. Header was just confusing with the meters and the mass. We can just skip the units, and we know that if it's metrics, the work is in joule. That means you can put the value and you can put joules. Or probably in this case, I will just ask you to keep, or maybe this way, 600 times 9.8, because I can multiply 200 times 6. Okay, makes sense? Good question for the quiz. Okay, let me check, because I still, for example, this one. A variable force, changing, of, I can maybe 5 times x to the negative 2 pounds moves an object along the straight line when it is x feet from the origin. Okay, that means from x feet from the origin. Calculate the work done in moving the object from 1 to 10. Work done. That's what we have to do in this case. It's a variable cost, not cost, a variable force. How can we compute work? Everything is given from 1 to 10. How can we compute if it's not fixed, if depends on x? We do have the formula for the force. How can we compute work? Just integrate from 1 to 10, because we will be moving from 1 to 10, f of x dx. That's it. From 1 to 10, 5x to the negative 2 dx. Just like that. And we can, I can draw, no, I mean, we can, I was thinking to draw it for you. That's the force. This is x, and this is function like 5 over x squared. That means it's just the hyperbola. And from 1 to 10. I mean, we basically need that area, if I would like to use really theoretical concept of integration. But we know that this is like a distance times the force, distance times the force. And that's work. And everything is done from 1 to 10. And that's the function. Okay, and you know how to integrate. Okay, that's the question. Okay, because I think I type all of the question. We don't have to solve it, and I will let you go, but just this is the same. You can probably do it. Oh, what about this one? So something is that I typed this correctly. I didn't type this correctly. Question number 5. Oh no, okay. Shown, some weird English. Shown is the graph of the force function in newtons that increases to its maximum value and then remains constant. Okay, that's they just explain this curve. Increases and then constant. How much work is done by the force in moving the object from moving an object a distance of 8 meters. Okay, that means from 0 to 8. Yeah, that's also a nice question. That's the force. That means I don't have the formula, but I still know that I have to integrate from 0 to 8 my function f of x, because it's changing. That's mean what will be the integral from 0 to 8 of this function? I can maybe divide. Do you think it's just the area under the curve? This will be under f of x. Okay, who can tell me what's the area? I think we can count this. Oh, okay, we have a triangle, which we have a triangle, which the area will be 1/2 times 4 and times height. Really good. Oh, we even have and we do have a rectangle. Base is 4 times height. That's what Jacob said, and Abdullah, 2 times 30 and 4 times 30. Perfect. Can you tell me the units? This work will be in joules or yes, because it's metrics. Perfect. Okay. Okay, that means at least I want you to know how to compute the work. I mean, we can have complicated questions, but this is also could be tricky. And I also have I have actually 2. This is similar idea, but it's actually no formula, no graph, just the value from the table. Okay. The table shows the value of the force function, where x is measured in meters, and f of x, which is the force, is in newtons. Use the midpoint rule, I can show you, to estimate the work done by the force in moving the object from 4 to 20, which actually we do have a data from 4 to 20. Okay, that's what I will do. We can probably see everything, but let's plot these points. We don't have to, but I just want to. Okay, that means this is x, and that's force. That means when x is 4, the force is what values we have. I'm just looking 5. Okay, 5. How can I do it? Let's do this way. A minus x squared. Maybe, maybe. Okay, that means for 6, we can see for 6, we have 5.8. 5.8. Yeah, I'm just drawing these points. For 7, we have 8. What is it? No, for 7, wrong, for 8. Okay, for 8 we have 7. I'm just looking, that's the highest, right? I mean, we will have 7, and then 10, 12, 14, 16, 18, and 20. I just want to show you the idea. For 10 we have 8.8. For 12 we have 9.6. For 8.2 for 14, 6.7 for 16, 18 is 5.2, and 20 is 4.1. Okay, I kind of, okay. Oh, yeah, looks like it is negative. Looks like x squared, or maybe like, yeah, if I will connect, it will be parabola, but it's shifted. But okay, no. And now they ask again, in order to find the work, yeah, we have to integrate. Yeah? In order to find the work, I will integrate from 4 to 20 my force function. And since I have only values, I can do this for so many ways. Like, you probably remember the right-hand side endpoints, the left-hand side endpoints. But now they telling me the midpoint rule. That means I will consider that I need the midpoint, and I will not figure out, that means I can consider that this will be the midpoint for that interval. Okay, and then this is the interval, this is the interval, and this is the interval. That means these dots are the midpoints. Okay, that means theoretically I'm kind of creating the midpoint will give me the height. The midpoint will give me the height. The midpoint, that's the midpoint, and this is the midpoint, will give me the height. Because normally the function looks, I can kind of, yeah, that's my function. That means how can I approximate the area under? I can, of course, I can use so tiny intervals, but if they're saying midpoints, then I'm just creating 1, 2, 3, and 4 intervals. Okay, and what I have to do, I have to just find the area, because again, integration means the area under the curve. That means we need the area of this rectangle with the midpoint 6, with the midpoint 10, and it's pretty much good approximation. That means this integral, okay, I can write it again, from 4 to 20, the integral, the only thing that I can do, I can approximate. And I will have, okay, what's the area of the first rectangle? And I'm using midpoint and 4. Can you tell me what's the area of the first rectangle? I need base times the height. That's me. What is base? How many units we have in the base? 4. For each of them is 4. That means we have 4 times the value for 6. Yes, 5.8. Thank you. And then 4, that means this will be the height. This will be the height. And then 4 times the value for 10. And then 14, not 14. 4 times the value for 14. And the last one is the value for 18. And again, you don't even have to I mean, if it's your homework question, you may multiply everything and add together. But if this will be a quiz question, you can leave it like that. Okay, you can put, instead of f of 6, you can put that value, and then we need this value, 14 and 18. Okay, but just the idea how to get the work, we will integrate the force, but having a formula, having a graph, or having a value from the table. Okay, that's mean I will, yes, I just want you to remember, maybe no, maybe you can tell me what formulas you've learned today. No, I think, Heather, we have to draw it. We have to draw it, or because I copy exactly from the textbook, the question. If I will put this question, I will tell you that I am expecting number of intervals 4. Okay, I know you asking, yes, yeah, because I just copy directly from the textbook, and I think will be easier for students, for my students, to have the number, because you're right. How do I know? Yeah? That means I will say, and then you will take the whole distance between 4 and 20, which is 16, divide by 4, you will get a delta x4. Yeah, I will give you the number of rectangles. Okay, please type in the chat box the formula for the work, and I will let you. Force times the distance. Okay, that's perfect. What happens if force is changing, if force is the variable? Can you type the formula? Okay, the integral. Yes, Brian said yes, Abdallah said integral. Yeah, you can even say integral. Yeah? Integral of, you will integrate on the given interval. And just be careful, you can double check the question, like what interval we're using, especially with that spring. Okay? Okay, that means no more like water, and we will skip that question. As I said, if you would like, you can check the solution but only the question that I solved with you, you can expect them on the weekly assignment and the midterm. Okay? Thank you very much. And tomorrow I will also try to make it, because we have another application, I will try to make it as simple as possible. Okay? Thank you. Thank you very much. And please no, don't be scared. Thank you. Thank you very much. Thank you. Check these questions again. Thank you. Oh, I have my lots of notes. Oh, thank you, Heather. Thank you. You too.